Bonjour, bonjour, bonjour tout le monde. Welcome back to another differential geometry reading stream. This is episode 28 now, and I'm Anthony, obviously. We've been reading from Differential Geometry by Erwin Kreisig. And if this isn't your first time watching one of these, then you already know that I read and talk about more than that. But it is mostly about differential geometry. So we are going to be reading starting on page 208, which is in chapter 6, formerly called mappings, but in my opinion it should be renamed conformal mappings. By the end of this chapter, we're basically going to have looked at different kinds of map projections. So it's like a flashback to 7th grade social studies geography class, day 1, talking about how different types of projections of maps of the world, say, will not be exact, obviously, because if you want a perfect quote-unquote map of the Earth, you would have a scale model in the shape of the Earth, which, as we know, is not an exact sphere, all this kind of stuff. But even then, there will be things that might not be accurate as far as representing the Earth. Big example, I've got this globe from the top of one of the bookshelves over there. And we've got Antarctica, which is really small looking down here at the bottom compared to the rest of the world. So Australia, Antarctica, and China are all basically the same surface area on this globe. We all know that's not the case in real life. But then last section we looked at the Mercator projection, and that does a little bit better justice to the size of Antarctica compared with the other continents. But some people would prefer the projection of that globe, say, because if you're a little kid or someone looking at a globe, you want to look at maybe the different political boundaries of the various countries on the world. You don't really care. You'd be like, okay, great, that's awesome that Antarctica is huge, but I want to see the different countries, right? So that's different reasons why you would go with looking at different projections of maps, right? That's something that, you know, you get, like I said, first introduced to day 1 of grade 7. Here we are in differential geometry. This is page 208, section 66. And today, hopefully, I'm going to read a couple of sections on equiareal mapping. So recap again if this is your first one or you haven't watched in a few weeks, months, whatever. This chapter could be called conformal mappings, right? Conformal mappings are ones where angles are preserved. Now we're going to get into equiareal, so the mapping is going to probably preserve area, right? That's what we're getting into today. But before I really get into it, this is something I haven't done in a while, and that is reading viewer comments. So today we're going to start off with an OG. I'm a little bit behind on replying, incorporating these comments into the regular flow of these episodes, but I printed out a few of them and then I put them in these envelopes here. So we've got the first one. Figured I'd cut this open. I don't really use this to cut letters open. And this is from Vanderhagen the Stampede. This is on 2 videos ago now. Actually, no. By the time this is coming out, this is 3 videos ago now. So we have the first one. My native language is Brazilian Portuguese, but I've been studying and using English as my primary language for about 10 years ago now. Nice. As for my nickname, it's actually a funny story that happened by chance. Nice. We go on here. We have this example of using algorithms to implement simulation of a special kind of dice or die for a role-playing game or similar project. I feel like this is kind of like along the lines of Dungeons and Dragons, which honestly, I am not a board game guy. I am not a Dungeons and Dragons guy, but I'm all for it. I'm all for, you know, programming that involves a lot of math on the back end. So I'm all for it. And we've got the Louisville surface seems to be related to the torus, which is also connected to the hop vibration. Vibration. I'm wondering if the Louisville surface can be thought of as a type of hop vibration or something entirely different. You know, one of these days I'm going to print out every single Vanderhagen the Stampede comment and I'm going to put them all together with the notes that I have for all these episodes, because, you know, it makes like a nice appendix, you know what I'm saying? It's always interesting to read the stuff from regular viewers, such as Vanderhagen the Stampede. So thank you once again for all of your insightful, thought-provoking comments here. But now we're going to get to the viewer comment of the week. Vanderhagen the Stampede has won the most viewer comments of the week, possibly because statistically they've commented the most. But here we have one that I chose for this week's viewer comment of the week here. So let's open this up and see which one I picked here. It's kind of like, you know, like the Emmys or the Grammys or whatever, right? This is from Adam RT2IR. And there are two comments here. The first one here is the viewer comment of the week. And this is on my video 2 episodes ago now when this is coming out, which is the Bergman metric and kernel complex analysis differential geometry crossover episode. We have one of my favorite types of comments, which is a correction, a pointing out an error on my behalf. These are the kinds of comments I appreciate the most from you guys. Shout out to Adam RT2IR. We have, you pronounce Banach wrong. The CH is pronounced like an H, which is a voiceless velar fricative. I'm probably pronouncing velar wrong, but we're going to get into this in a sec here. I think the word house in English has a pretty close H, which is a voiceless glottal fricative. I hope this helps. And you will see that, or you may have just heard that I tried to correctly pronounce Banach, which is different from how I did in that video, which is Banach, right? CH as in chord, let's say, as in the chord of a circle, chord on an instrument, musical instrument. So I'm going to refer now to this book here, which I think is a great kind of like gloss over of linguistics. It's called The Wonders of Language, or How to Make Noises and Influence People. I really appreciate the linguistic detail of the exact phonetic pronunciation of these names, which are not American English, you know, whatever, right? So I'm going to start off here. Hopefully I'll have this on the screen, but we have, I would say, a mid-sagittal section view of the mouth and throat, with particular attention to anatomical structures which are conducive to speaking. And it's all nicely labeled here, but I would particularly point out features such as the labial area, the dental area, the alveolar ridge, the velar area, and the glottal area. So we have these terms in our viewer comment of the week: voiceless velar fricative, voiceless glottal fricative. Well, by looking at this anatomical cross-section, we have velar and glottal referring to these areas of the mouth and throat which are being engaged in producing these particular sounds. Specifically, we have these H sounds. So the H is the symbol which, when you read these words, you're supposed to be associating with these particular sounds, right? So I obviously was incorrect when I look at the symbols and I see this CH and I think, oh, we're going to use the sound K. We're going to say Banach. But really, when I see those characters, I should really be saying banah. So I probably didn't pronounce it properly that time, but a fricative specifically is when the air becomes turbulent passing through that little groove in your tongue and the gap between your tongue and your top teeth, creating a high frequency noise. Okay, that's what it says here. But really, I think what's helpful, and we've got voiceless, voiced, and nasal sounds, of course, which I won't get into the details of, but I think all this stuff is honestly really interesting. We're just going to jump ahead to a summary table of English consonants here. So we've got a voiceless velar fricative, and as you can see on this table, there is no exact, this is English consonants, right? There's no exact symbolic representation here. And you can see right next to it on the table, though, we have what was mentioned, the voiceless glottal fricative, which is in the word house in English, which is close, right? So we're really seeing this here. Banah. I don't know. I appreciate it, Adam R22IR. These are the kinds of things, these are the comments that I really appreciate in this series. This is kind of what this is all about, right? And I'm all for it. So we also have another really insightful comment from Adam RT2IR, which is on my very first, you could say, differential geometry reading stream video back in February now, which is asking ChatGPT an easy differential geometry problem. It was from the beginning of this book, the Theory of Curves chapter. Honestly, the comments section on that video is turning into almost like a Stack Overflow style, like continuous refinement of just great insight into this problem, just adding more detail. And yeah, so we have, there's no continuous bijection from the interval 0 to 1 including 1 to 0 to 1 including 1 squared, by the way. The simplest argument I can come up with is as follows, using dimension theory. Write the interval from 0 to 1, which includes 1, as countable union of compact intervals capital I sub n. Then the restriction of the map to capital I sub n is a homeomorphism onto its image. So the interval 0 to 1 including 1 squared is a countable union of closed one-dimensional spaces. By the countable sum theorem, we obtain that 0 to 1 including 1 squared is one-dimensional. Contradiction. Here dimension means inductive or covering dimension, which are the same in this case. I'm going to have to look up the countable sum theorem after this. But anyways, this is, like I said, I really respect and appreciate the knowledge that the viewers of these episodes really seem to have, which often, as we've seen from Adam RT2IR and of course Vanderhagen the Stampede, it often surpasses my own understanding, and I love it. I'm all about it, you guys. So I hope you guys liked the whole printing it out and getting your guys' comments out of envelopes this time around. But just as a reminder, your comments could be featured like theirs were just now in a future episode. So leave a comment below, like, comment, subscribe, ring the bell notification, all that good stuff. But let's keep going. So yeah, like I said, we are now going to keep reading from Differential Geometry by Erwin Kreisig. We are in section 66 in chapter 6 on page 208, equiareal mapping. An allowable mapping of a portion S of a surface onto a portion S star of a surface is called equiareal if every part of S is mapped onto a part of S star which has the same area. The necessary and sufficient conditions for a mapping to be equiareal are as follows. Theorem 66.1. An allowable mapping of a portion S of a surface onto a portion S star of a surface is equiareal if and only if at corresponding points the discriminants G and G star of the first fundamental form of S and S star, when referred to the same coordinate systems on S and S star, are equal. So of course, quick note, in allowable mapping, We have derivatives that exist as we need them. We're not going to have any tricky pitfalls. And yeah, when we see G just like that with no subscript indices, it's referring to a discriminant of the first fundamental form, as opposed to if there are subscript indices. So if we had like a G sub alpha beta, then those are referring to components of the first fundamental form. So for those of you who are just dropping in for the first time, and now we have a proof of theorem 66.1. The proof is analogous to that of theorem 57.1. Instead of the integral of the arc length, one has to consider the integral, which is mentioned in section 36, which is in the definition for the area of a portion of a surface as a double integral, which is capital A of capital H, where capital H is referring to the portion of the surface S, let's say. This area is equal to the double integral on capital U, which is the domain in the U1, U2 plane corresponding to H, where U1 and U2 are the coordinates on that surface S. We have the double integral on capital U of the integrand, the square root of G. There we have the discriminant of the first fundamental form. And the integral is du1 du2. And when referring back to this definition, we have that integrand, square root of G du1 du2, can be denoted d capital A, which is then the element of area of that portion H. So referring back to the proof of theorem 57.1, that was probably 4 episodes ago now. So we have an allowable mapping of a portion S of a surface onto a portion S star of a surface is isometric if and only if at corresponding points of S and S star, when referred to the same coordinate systems on S and S star, the coefficients of the first fundamental forms on S and S star are the same. G sub alpha beta equals G star sub alpha beta. Plug everything in, make sure that the integrals are all equal, and so basically now for the proof of theorem 66.1 is saying basically just do the same thing. So awesome. We're going to continue on. Furthermore, we have theorem 66.2, which has 2 parts. The first being every isometric mapping is equiareal, and the second part being every equiareal and conformal mapping is isometric. The proof of theorem 66.2 is as follows. For the first part, we have that it follows immediately from the preceding theorem, theorem 66.1, in combination with theorem 57.1, which I mentioned, which I could see how that makes sense. For the second part, it has if the mapping under consideration is conformal, then by theorem 61.1, at corresponding points, when referred to the same coordinate systems on both surfaces, G star sub alpha beta is equal to nu in terms of U1 and U2, then times G sub alpha beta. And to refresh ourselves, this is from like 5 or 6 episodes ago now. Theorem 61.1, an allowable mapping of a portion S of a surface onto a portion S star of a surface is conformal if and only if, when on S and S star the same coordinate systems have been introduced, the coefficients G sub alpha beta and G star sub alpha beta of the first fundamental forms of S and S star, respectively, are proportional, namely G star sub alpha beta is equal to nu in terms of U1 and U2, then times G sub alpha beta, where nu is positive and alpha and beta can be 1 or 2, respectively. So, okay, we obviously see how theorem 61.1 is roped into this. From this, we have G star equals nu squared times G. In consequence of theorem 66.1, G star equals G, hence nu squared equals 1. Now, since G sub 1 is greater than 0, this is referring to a component of the first fundamental form now, like I said, as well as G star sub 1 is greater than 0, or positive, nu equals positive 1, and consequently, G star sub alpha beta equals G sub alpha beta. That is, the mapping is isometric, for which refer back to theorem 57.1. So, thus concludes the proof. We will now study equiareal mappings of surfaces of revolution into a plane. We obtain a surface of revolution by rotating a curve capital C about a straight line in space. That line is called the axis of revolution of that surface. We rotate a curve capital C represented by x1 equals a function lowercase p in terms of coordinate u2, which is positive, x2 which is equal to 0, and x3 which is equal to a function lowercase q in terms of coordinate u2 about the x3 axis of the Cartesian coordinate system in space. The surface of revolution S thus obtained can be represented in the form vector x in terms of coordinates u1 and u2, which is equal to, entry-wise then, the function p of u2, then times cosine of u1, then p of u2, then times sine of u1, then q of u2. The curves where u1 is equal to a constant are called meridians, and the curves where u2 are equal to a constant, parallels of S. So now we can really appreciate how all of this math is actually then related to things like maps of the Earth, right? Because these terms, meridians and parallels, we use all the time. Latitude, longitude, when you're reading maps, doing cartography, right? So great, let's move on. Theorem 66.3. A mapping x1 star equal to a function x1 star in terms of u1 and u2, and x2 star which is equal to a function x2 star in terms of u1 and u2 of the surface S, represented by the previously given vector parametric form above for x, into a plane S star with Cartesian coordinates x1 star and x2 star is equiareal if and only if the corresponding Jacobian capital D over bar satisfies that capital D over bar squared is equal to p squared times the quantity p prime squared plus q prime squared, closed quantity, where here primes denote derivatives with respect to u2. The proof is as follows. On capital S, we have that g sub 11 equals p squared, g sub 12 equals 0, and g sub 22 equals p prime squared plus q prime squared, and therefore g is equal to p squared times the quantity p prime squared plus q prime squared, closed quantity. The discriminant of the first fundamental form of the image plane S star has the value 1. By means of the previously given mapping in terms of x1 star and x2 star, we introduce in S star the coordinates u1 and u2 of S. Then that discriminant is multiplied by capital D over bar squared, for which we can refer back to 28.4, which is from obviously section 28, but theorem 28.3 specifically, which is considering the transformation behavior of the discriminant of the first fundamental form. Hence, afterwards, g equals g star. That is, the mapping is equiareal, and we can refer back to theorem 66.1. Important applications of this theorem will be considered in the following section. Speaking of, we are in the following section, which is section 67, equiareal mapping of spheres into planes, mappings of Lambert, Sanson, and Bonn. The practical importance of mappings of the sphere into the plane has already been discussed in section 65, where we saw the stereographic projection. We will now apply theorem 66.3, which we just proved, to some interesting types of equiareal mappings of a sphere S into a plane S star with Cartesian coordinates x1 star and x2 star. Setting in the vector parametric representation of the surface of revolution previously given in 66.1, consider the following representation where we have p of u2 equal to r times cosine of u2 and q of u2 equal to r times sine of u2. We thus obtain the representation which has been referred to throughout this book, but is first from section 25, which I'll hopefully pop up on the screen right now, of the sphere S of radius r with center at the origin of the Cartesian coordinates in space. In consequence of theorem 66.3, the Jacobian capital D over bar of an equiareal mapping of S into the plane S star must now be equal to positive or negative r squared times cosine of u2. Lambert made the first general investigations of mathematical cartography. The so-called Lambert projection, however, was already known much earlier. I think there's a similar case with Mercator where, and I think I mentioned this possibly in the last episode, but it's almost like the opposite of what I just said about Lambert, where Mercator came up with the projection, but then the actual mathematical details didn't come up for a couple hundred years afterwards. So anyways, in terms of the coordinates just introduced, namely those above at the beginning of this section and then the vector parametric representation at the end of last section in 66.1 and then 67.1, like I just said, the Lambert projection is of the form x1 star is equal to r times u1 and x2 star is equal to r times sine of u2, where u1 is greater than negative pi and less than or equal to pi, and u2 is greater than or equal to negative pi over 2 and less than or equal to pi over 2. Since the corresponding Jacobian is capital D over bar equal to r squared times cosine of u2, the Lambert projection is equiareal, for which refer back to theorem 66.3. The image of the sphere is a rectangle whose sides have the lengths 2 pi r and 2r. The mapping, which is 1 to 1, with the exception of the poles of the sphere, point of infinity, can be geometrically obtained by projecting every point of S on a cylinder S star in contact with S along the equator by means of projecting lines parallel to the plane of the equator and passing through the axis of rotation of S star. By cutting S star along the line corresponding to U1 equal to pi and bending it into the plane, we obtain the desired image of the sphere S. The images of the parallels and meridians are straight lines. The latter are equidistant. The distance between the former decreases with increasing latitude. We now consider the mapping of Sanson, which Sanson obtained from Lambert and used for construction of maps in presumably 1650. This mapping is given by x1 star equal to r times u1 times cosine u2 and x2 star equal to r times u2, where u1 is greater than negative pi and less than or equal to pi, and u2 is greater than or equal to negative pi over 2 and less than or equal to pi over 2. It is equiareal since the corresponding Jacobian capital D over bar is equal to r squared times cosine of u2. The images of the parallels where u2 are constant are parallel straight lines where we have that x2 star are constant. The distance of those images is the same as the spherical distance of the corresponding inverse images. The length of any segment of the images of the parallels equals the length of the corresponding inverse image. We finally consider the mapping of Beaune, introduced by Beaune in the 18th century and frequently used in cartography. It is defined by r star equals r times the quantity pi over 2 minus u2 closed quantity, and alpha star equals a fraction with the numerator of u1 times cosine u2 all over a denominator of pi over 2 minus u2, where u1 and u2 are the coordinates on the sphere S, defined as given in section 25, hopefully that's on the screen now, and r star and alpha star are polar coordinates in the image plane S star. The discriminant of the first fundamental form of S star is g tilde equal to r star squared. When u1 and u2 are introduced as coordinates in S star, in consequence of the transformation behavior of the discriminant g of the first fundamental form, as given by 28.4, g tilde is multiplied by the square of the Jacobian capital D over bar equal to r cosine u2 all over pi over 2 minus u2. We therefore obtain g star is equal to r squared times the quantity pi over 2 minus u2 closed quantity squared, then times capital D over bar squared, which is equal to r to the fourth times cosine squared of u2, which is equal to g. That is, the mapping of Beaune is equiareal. The images of the parallels u2 equal to u naught superscript 2 equal to a constant are arcs of the circles r naught star equal to r times the quantity pi over 2 minus u naught superscript 2 closed quantity. The image point of the North Pole is the center of these circles, for which refer to figure 80 below. The length of an arc of the image of a parallel is equal to the length of the corresponding inverse image. We now come to problem 67.1. Investigate the mapping of Collignon, where we have x1 star equal to 2 times the square root of 2 all over the square root of pi, then times r times u1 times the sine of pi over 4 minus u2 over 2, and also x2 star, which is equal to r times the square root of pi, then times the quantity 1 minus the square root of 2 times the sine of pi over 4 minus u2 over 2, close all quantities. The solution to problem 67.1 is as follows. Since partial x2 star partial u1 equals 0, we have that capital D over bar is equal to partial x1 star partial u1 times partial x2 star partial u2, which is equal to 2 times r squared times the sine of pi over 4 minus u2 over 2 closed quantity, then times the cosine of pi over 4 minus u2 over 2 closed quantity, which is equal to r squared times the sine of pi over 2 minus u2 closed quantity, have a little bit of trig identity is going on there, equals r squared times cosine of u2. The mapping is equiareal. The north pole of u2 equal to pi over 2, for which refer to the coordinates which were introduced in the previous two sections that I just read. The north pole is mapped onto the point x1 star equal to 0 and x2 star equal to r times the square root of pi. The south pole corresponds to a segment of the straight line x2 star, which is equal to negative square root of pi, then times the quantity square root of 2 minus 1, closed quantity, then times r. This segment has the length 4r times the square root of 2 pi. The meridians are mapped onto segments of straight lines, as can easily be seen. The image of the sphere is an isosceles triangle whose base and apex correspond to the south pole and north pole respectively. The parallels are mapped onto segments which are parallel to the base. And being that the next section, section 68, on conformal mapping of the Euclidean space is longer than just 2 or 3 pages and is also the end of chapter 6, and being that we're already a little bit long with the reading plus the viewer comments, I'm going to end it here. And so check out the fit for today. We're rocking one of my favorite blazers that I've got, the Shepherd's Check brown blazer, green vest on the classic white button-down collar, long sleeve shirt with the blue foulard tie, and then we've got the tan strap gold tank Peugeot gold watch with the gold signet ring. And then I'm rocking these with actually the dark brown tweed pants. If you saw the Sigmund Freud post in my community tab, the jacket with that one that matches these pants is a little bit tight. Like if I were going to do some push-ups or some pull-ups in that jacket, I might rip it. So I was like, if I'm layering with the vest, I'm going to throw on this Shepherd's Check blazer, and I think it goes really well with these pants. I would rock these probably with the brown boots, the Clark's Chukka boots. Simple black socks, but if you wanted to really spice it up, you could probably throw on the burgundy red socks, and that would take this to a whole other level. But I'm going to end it there. See you guys in the next one. Peace.